the kinematics equations. We've got these equations here. We're gonna be on this topic again today, and then by next Wednesday, then when we come back, we'll be on the vectors for one day. We should finish that next Wednesday, and then the Monday after that, we start chapter 4, which is two-dimensional kinematics, and then we do that. We do projectile motion, kinematics of circular motion, and after that, the Monday after that is your first test. So already it's coming up, so get ready. The first test will be chapter 1, which is the units, chapter 2 and then 3, which is the vectors. Okay, so now we want to add the equations of free fall to this, because free fall is an example of constant acceleration. Constant acceleration. So in the case of free fall, we have once something leaves your hand and now it's in the air, free fall takes over, concept of free fall, and the acceleration is equal to negative 9.80 meters per second squared, or negative 32 feet per second squared, which is the acceleration due to gravity. So a lot of times this is also written as negative g. Right? So then we can use these equations and then replace the a by negative 9.8. So you just have to look at the wording of the problem. If the wording of the problem is in meters, you use the 9.8 number, and if it's in feet, you use the negative 32 number. And then x I'm going to replace by y because it's in the vertical direction. Then a replaced by negative 9.8. And here replaced by negative 32. And here replaced by negative 9.8. Now here, there's nothing to replace by, because remember the fourth equation, the a is already missing, so we don't need to replace by anything. Just change it to this. Okay, so now we can do some variety of free fall questions, so I'll probably do some of that, then maybe come back and do another example of a regular acceleration problem. So this one is going to be a free fall question. Okay, so a person throws a ball from the top of a 120 feet building, and it takes 3 seconds to hit the ground. What is the initial velocity of the ball, and what is its final velocity? We could also say what is the initial velocity of the ball? What is its final velocity? What is the maximum height it rises to? Can we ask other questions?
How long it took to hit the ground?
That one is given.
Oh,
Any other questions we can ask? How long it took to hit the ground? So how long it took to hit the ground is given. The initial height is given. I think that's all. Initial velocity, final velocity, and then the maximum height. That's pretty much it. Okay, so now what's the best way to get A? Which of these equations? So the next thing is to say, okay, is it the first equation the most effective, second, third, fourth? This is also 1, 2, 3, 4. Okay, so we are given the initial, well, we're given the height, we're given the time. I think it's the second equation is the best one, right? We're given the y final, y initial. V initial we don't know, but the time we know. So yeah, the V initial, that's the best one. And since it's in feet, we should use this version, right? In feet. So then I'm gonna have the building. I'm gonna put my XY axis at the bottom of the building. Right, and then here you are. We don't know if you're throwing the ball up or down. It doesn't tell us, we just know that you're throwing it. So let's say you're throwing it up. Right, so then if I put my coordinate at the bottom of the ground, right, where the ground is, right, and then the y initial is gonna be what? Y initial is 120. So my equation is y final is y initial plus v initial t minus 16t squared. Y final is gonna be 0 because that's when it hits the ground. Y initial is 120. V initial I don't know. Right? T is 3 seconds. So T, V initial minus 16 times 3 squared. So actually with that equation, you can determine if V initial is negative or positive. That equation will tell you if V initial is negative. If V initial is negative, that means you threw it up. If V initial is negative, you threw it down. Right? If V initial is positive, you threw it up. So this one goes over here, 16 times 3 squared minus 120, right? And then you divide by 3, right? So then 16 times 3 squared, that's a 9. 9 times 16, that's gonna be 9 times 16. 144 minus 120 over 3. Did I do that right? 9 times 16. 4, 5, 9, carry the 5. 14. Yeah. 44 over 3. 8. So because it came out positive, that means you threw it up. So in other words, by giving you the total time that it took, that's kind of telling you whether or not you threw it up or down, right? Because if you threw it down, it would take shorter amount of time for it to hit the ground, right? So if it only took, let's say, 2 seconds to hit the ground, what would happen? There would be a certain limiting case, right? 2, you put 2 here, then you would put 2 here, and of course you would put 2 here, right? 4 times 16, 64. Minus 120, negative. Right? So if it only took 2 seconds to hit the ground, that means you threw it down. Right? But because it took 3 seconds, that means it must have gone up first and then come down. Right? Interesting, right? So the time is determining whether or not you threw it up or down. That makes sense, because if you throw it down, it's going to take shorter time to hit the ground, right? Okay, now that we know the V initial is 8, we can answer what is its final velocity. So which equation should I use for that? We could use this, we could use this, but the quickest one is probably this one, you know?
Yeah, fine.
Yeah, you just go. V final is V initial minus 32t. But remember, use the 32 version, right? So it's going to be 8, and then the t is 3. So of course it's going to come out a big negative number, right? Because since it's going down, that means the final velocity, this is the final velocity just before it hits the ground, just an instant before it hits the ground. So 8 minus 96, negative 88 feet per second. Okay, then the next one is going to be C. What is the maximum height it rises to? Okay, so that means this height from here to here. H max. Okay, so then what is that? What do we know about the velocity when it gets to the maximum height?
0.
Yeah, the final velocity is momentarily 0, but only for a split second, right? So at that point, V final is 0. So we could use, you know what, we could use the best equation to use is the third one. Because the third one that is missing t in there, right? Doesn't have t. So we don't really know the time that it takes to go to the maximum. We don't have that. And it's not even asking for the time. So the quickest way to not worry about the time is just to use the third equation. Right? Remember to use the 64 version to a 2a, right? So then you're going to use V final is 0 at the top, V initial is 8, Y final minus what's Y initial? 120, right?
Oh.
There you have it. So without needing the, it should be squared, yeah. Good one, it should be squared. So this 0 squared, 8 squared, minus 64, right? So I don't even need to find the time. Right, so then you're going to have 64, then take this to the other side, 64, and then this one goes to the other side, 64, 64 cancels, Y final equals 120. Oh no, sorry, hold on. This became 1 plus 120. That's weird. So it only went up 1 feet. Wait, is that right? 8 squared, 64, 1.
It's not a very fast initial speed.
Yeah, that's a very slow speed. So barely goes up like, right? I mean, that's got to be really slow. 8 feet per second. It's like it barely. That means it barely goes up 1 foot. 8 feet per. It's very slow. Like that. 8 feet per second is about what? 3 miles an hour. Something like that. Huh? Oh, yeah. You're right. It should be feet. Yeah, so 121 feet. We got the maximum height and we answered all of them. Question? Okay. Oh, because the problem was given in feet. See feet? That in and of itself, that's it. That tells you to use feet. Yeah. Good question.
The initial would it be positive or 8 plus 32?
See? The
The
initial?
initial to where the
Oh, I think I meant to say V final here, right? V final is 8 minus 32.3. Yeah, negative. That's V final. It's going down. Okay, now let's add another part. So assume instead of the ground, okay, so it says, assume instead of the ground there's a river at the bottom of the lake and that the ball enters the river and accelerates at a rate of 10 feet per second squared. If the river is 50 feet deep, how long does the ball take to hit the bottom of the river? And what is its final speed when it reaches bottom of river? So that's the other questions we can ask. So now instead of the ground, it goes into a certain body of water, right? Lake or river. So now you're given the depth of the river, and you're told that when it enters the river, it continues accelerating, right, at 10 feet per second squared. Yes. Does the ball take to hit the bottom of the river? So how long does it take the ball to hit the bottom of the river, and what is its final speed? So let's see if this fact that is given, does that even make sense? When the ball enters the river, can it continue speeding downward at 10 feet per second squared? So here's the river. When the ball goes through the river, so what does it mean to say that it's accelerating at 10 feet per second squared? So how do you understand that? Does that mean that it's slowing down or speeding up?
Speeding.
Huh? Speeding up? You said it's slowing down?
Yeah, its initial speed is downward, and the acceleration is upward, so it's slowing down.
Yeah, so he's saying the speed is down when it enters the river, but since the acceleration is positive, it's slowing down. But is that what you read from the wording?
No, because it means it goes faster.
Yeah, so the wording is very careful. You have to read it very interestingly. If the acceleration was positive 10, I believe the wording would have been the ball decelerates at a rate of 10.
It should be decelerate.
Yeah, it should have been decelerates. So then we know that the velocity is down, the acceleration is up, and now the ball decelerates because it slows down. So anytime the velocity and acceleration are opposite, you're decelerating. So the fact that it said accelerates at a rate of 10, but it didn't say negative 10. It wants you to put the negative,
Cheeky.
right? So whoever is the test writer for that wants you to know you have to put the negative. So who would be the test writer? Me, the mean evil guy, right? So if it accelerates, you have to know that the speed is down and the acceleration is also down, right? So could that happen? Can a ball enter a body of water and continue accelerating? In which case would that happen? What is this ball made of? Is it a wood ball, cotton ball, metal ball? Huh? Metal? Would metal ball keep speeding as it went in water? Or would it slow down?
Yeah.
What's the physics of, this is physics 2, but we might as well just quickly review from physics 11, review the little bit of buoyancy, all right? So we don't need to get too much in depth. When something enters the body of water, you got its weight, and you got the buoyant force, right? And the buoyant force depends on the density of the material, right? So if the material is denser than water, right, which is like metal, rock, or anything like that that's denser than water, that means the buoyant force is going to be less than the mass of the weight of the water, because water is not going to be able to sufficiently apply enough buoyant force to equal its weight. So in that case, the weight minus the buoyant force is still going to cause it to accelerate down, but at an acceleration less than g, right? So is this acceleration less than g? Yeah, because it's g is 32 feet per second squared. Remember, don't worry about 9.8 now. It's feet per second squared. So since it's accelerating less than g, yeah, this would happen in all cases where the object is made of a material denser than water. So the ball can be rock, anything, aluminum, metal, any other metal pretty much. Okay, how about if it said the ball enters the river and slows down or decelerates at a rate of 10? Could that happen? Yeah, it could be a material less dense than water, like wood. So the wood can enter, but in that case, the density of water is more than density of wood. So it's going to cause it to decelerate and maybe might not even hit the bottom of the lake or river, right? The wood might come and stop somewhere.
Yeah.
And then after that go up. Go
Not
back
this
up.
case, None of this case. None of this.
No, not in this case, yeah. But it might come down, reach a stop, and then go back up and then float.
Yeah.
You know, that could happen
Yeah,
too. So if it said therefore if it said decelerates at 10 feet per second squared, then the object is less dense than water. Okay. How about if it said it enters the river and reaches the bottom, goes through the river at constant speed? Can that happen? It's not very often that would happen, but yeah, you could do it. You could have a certain material that's about the same density as water, you know?
And it constant speed.
Huh?
And then it moves at a constant speed once it hits.
Yeah. Like it could be a body you're trying to hide in the water, like a dead person. You can wrap them up and then put a lot of foam in there. You know, so a person is usually denser than water. Then you put foam. I don't know why you would, because if you were a criminal, you want to make them more denser, right? So they can sink faster. But if you put foam in there, so their density might be just about as dense as water. So then when they hit the water, they would sink at constant speed. So you can create any of the possible scenarios that you want. Either slow down, speed up, or constant speed. Okay, now that we know what it means, so how do we solve this? We know the velocity upon entering the water. The height of the depth of the water is given. How long does the boat take to hit the bottom of the river? So which equation should I use?
So still
How long does it take to hit the bottom? Should we solve that first, or should we solve the final velocity first? I think we can do either one. I think we could do either one, right? If we're trying to do the time first, we should use which equation?
VF is equal to VI.
I think it should be if we're trying to find the time first, which of the four equations is missing V final? The second equation, right? That's why the second equation is the most often used equation, because it's missing V final, and in a lot of cases we don't know V final. So we can use the second equation to find T. Then once we have the T, we can always solve for V final, you know? So the second equation, we can have Y final is Y initial plus V initial T. So what should I put for the acceleration? Okay, here I have to be a little careful. For now, let me just write it as half AT squared, because I'm not gonna write negative 16T squared, right? Can't use 16 anymore. We can't use acceleration is negative 32 anymore. So let me just write it as a general equation, then determine my axis. So here's the top of the river. Here's the initial velocity when it enters the river, negative 88, right? So then we don't know the final velocity when it hits the river. So I'm gonna put my axis at the bottom of the river, right? What else? Oh, then which direction is the acceleration? Down or up?
Going up. Accelerates at
Accelerates at 10, it's down.
accelerate. You mean accelerate, not decelerate.
Yeah,
Okay.
accelerates is down because it's going down, and if it's accelerating, it's down also.
Okay.
Yeah. Okay, now I can put negative here because my axis is at the ground, at the bottom of the river, right? So XY So now what's gonna happen? What's y final? Since my xy is at the bottom of the river, right? My y final is 0. My y initial is what? The depth of the lake is 50. B initial is negative 88. A is what? Negative 10. Right? Negative 10 feet per second squared. So I'm going to put here negative half 10, right? That's why I put here half AT squared. This is the general equation for any acceleration. Right? Negative initial velocity, the acceleration is also negative because it's speeding up, right? So this part of the question is kind of tricky because you got to get the signs right, the negatives and that stuff. Okay, so now we're set to solve it. Right, and then I can move everything to the left side.
It should be negative 50, right?
Negative what? 50?
Yeah. 50.
No,
so
50.
The axis is at the bottom of the river. So
Oh, okay, alright, I see. You said 0 to the bottom of the river.
Yeah, because I put
Okay.
the axis.
Yeah,
If
yeah,
you
sure.
want to put the axis on the top,
That's the same.
which you could, like that,
Yeah, right.
so then the y initial will be 0, y final will be negative 50.
Yeah, it's the same thing. That's what I thought.
You see? So having 0, 50 and having negative 50, 0 is the same thing.
Yeah.
But you just have to be careful, you know. But I usually like to put my axis in the lowest point of the problem. That way there's less negatives to worry about. So now you have 5t squared plus 88 minus 50 is equal to 0. Now you can put this in the solver for your calculator and have it spit out the answer. Oh, this time doesn't have solver. So you have to put it into solver. So get used to using the solver so that you're doing this quicker. Yes.
I have a question.
Yes.
Well, would it be easier for me to insert equation to calculate the final speed first? Because in that calculation, we don't need to solve the equation. We just
So find the velocity first.
Yeah.
You
Then that
could.
equation we don't need to do the functions. Should be either in calculator.
Yeah, you could. I guess you're trying to avoid doing a quadratic
Yeah.
equation, right? Yeah.
I'll do that.
.551 second. Right? Now, how do I find the final speed when it reaches the bottom?
The first.
Back to the first equation, right? V final is V initial minus plus AT, right? So what's my, here again you have to be careful with signs. V initial is negative 88. A is what? Negative 10. And then the T is 0.551. Negative 93.51 feet per second. Which makes sense because it should be going faster, right? 93.51 feet per second. Now, if you wanted to do your way, find the final velocity first, how would we do? Which equation do you want to use?
First, we insert equation,
the third equation, right? So how would that work? Let's try. Negative 88 squared plus 2 times negative 10, right?
Yeah.
And then y final 0, y initial 50, and 88 squared. Well, if it's negative 88 or 88, it doesn't matter, right? So it's just gonna give you 7,744 minus 20 times negative 50. Yeah, it seems like with this method, there's
two speed, but since the final numbers
yeah, it's a plus or minus square root. With
Yeah.
this method, there's less chance of
calculating, but you need to figure out which one it forwards.
Yeah.
Since the ball is accelerating downward, so it can only be negative.
yeah. So in other words, when you're taking the square root, you have to decide if it's negative or positive. Whereas this one will already tell you that it's negative, right? Here you have to say, oh, okay, because it's accelerating downward, we know that it's gonna keep going down, and then the final speed is gonna be negative. So you're just gonna say negative square root of 87.44. That's gonna come out negative 3.51. And then you can use that to find the time. Then you can go to here. And then you can say negative 93.51, negative 88, plus, and then here this negative 10 times t. So that's the other way to do it. Use number 3. Then after number 3, you go to number 1. Then you do put the negative 88, negative 10t. Yeah, good problems. Okay, how about this? Let's say instead of accelerating at a rate of 10, it was decelerating at a rate of 10. So instead of metal, it was wood. So now the question can say, will the ball reach the bottom of the river? If it will, what velocity will it hit the ground? Or if it's not going to reach the bottom of the river, where is it going to stop? Right? Because it might be wood and it might actually stop. So now solve that. So instead of accelerating, it's decelerating. So answer the question, is it going to hit the bottom of the river? If it's going to hit it, what speed is it going to hit it? If not, where will it stop? Where in the river will it stop? Now choose which equation you want to use first. Which of the questions do you want to answer first? And then also choose the sign of your acceleration and velocity, you know, so you get the correct answer. So it's going to give you the closest answer to what you put here. If you put 1, still got like 10. No, no, no. If you wanted, if you were looking for a negative answer, you might put negative 10. And then it'll give you the negative answer. Stephen Poon Live, here. Hindi Sato. Timothy Tang. One of them doesn't make sense, or both of them don't make
One of
sense?
them, one of them says at the bottom it's negative velocity, the other one says that it's positive.
Oh, it's already going in, yeah.
It's like they just could be like, you know, if there's a reason why it's happening.
So if you put this one, which is the smaller time,
The smaller time you get a negative velocity.
which means it's still going down.
Yeah, which makes sense at the bottom. Yeah. But this one.
Oh, you know what that means? That maybe, yeah, it hits the bottom and going at negative 82.
Oh, well, how about this one?
Oh, well, if there was no ground to the river, you would just going
Deceleration
and then come back up and
is
return that point. Let's say the deeper was much deeper. Yeah, because it's gonna keep going, slow down, stop, and then come back. Yeah. Yeah, so buoyancy brings it back
So
up.
that means the force is going up.
Yeah, that's invalid. Yeah, exactly.
The
Invalid. Because,
Yeah.
because it's gonna hit the
force
ground.
is, it's pushing the force.
So it's positive.
So it should be positive.
Okay. So you're gonna change this to now you're gonna make the A positive, right? Then 5t squared minus 88t plus 50 is 0. We actually get two positive times this time, right? 0.5878. And in the second one we get 17.01 seconds. So which one of those two is the valid one? T1?
Yeah, T1.
T2 is too big?
T2 is
Well,
always,
So when it comes back around.
yeah.
Yeah, so if the river is like this, if it's going negative 88, it's going, and if the river didn't have a bottom, then it would just go, and then buoyancy would eventually make it stop, and then it would return to that same point. Yeah, so always when you're getting two answers, there's probably some physical meaning why you are, you know. And so yeah, this one is invalid because when it hits the bottom of the river, then it's done, right? So yeah, that's how long it's gonna take. Then you can use that for this.
Negative 82.
82 point. So the final is gonna be yeah.
Was that the quadratic equation from the last problem?
It's slightly different because the last problem the acceleration was negative 10, so this was negative 5.
Oh, okay. Okay.
Yeah, this one is slowing down, whereas the initial velocity is negative, but the acceleration is positive. So it of course changes the answers that you get. Yeah. So now the final velocity is negative 82. So if it hits the ground, if it hits the top of the river at 88, and now it's slowing down. So yeah, that makes sense. It's going at 82 down. So this problem does have quite a bit of good stuff in there where you have to worry about the buoyancy, the acceleration in the water, and then free fall. Okay, now let's do another one. This one will be just a general linear kinematics question. Okay, so a sprinter accelerates at a constant acceleration of 3 meters per second squared for some time, but it doesn't tell you the time. And then maintains constant speed for 8 seconds. Then accelerates at a rate of a, but it doesn't tell you the acceleration. And finishes a 200-meter dash in a time of 20 seconds. In a total time of 20 seconds. So I like this kind of question because it's got multiple stages to it, different things happening, and then the pieces of information that it's giving you seems kind of random, you know, here and there. Some things it's giving you, some things it's not giving you, right? So you could redo this problem in the SI again, give away some information, take away some information, and see how that changes the problem. Right? So this one, a good picture is important. Okay, so his initial velocity is 0. He's gonna accelerate at 3 until but we don't know the time here. So T1 we don't know. Right? Then once he goes at constant speed there. Constant speed. And then that one we are told the time, T2 is 8 seconds. Then after that, we are told that he accelerates again, but we're not given the acceleration. So acceleration is unknown, and all that's given is that the total distance is 200 meters. Okay, and what else? We're told that the total time is 20. So we're not really given T3. T3 we don't know, T2 we know, T1 we don't know, A we know, A1 we know, A3 we don't know, and of course A2 is 0, right? Acceleration in that second stage. And I think that's it. That's the picture tells 1,000 words, right? So what could it ask for? Well, it could ask for a bunch of things. You could say, what's T1? What is T1? T3? What else could it ask? They could ask, what was the speed during the second stage? What is the speed? Speed in second stage. And they could also ask the distance covered in each stage. Find D1, D2, D3. And they could also ask what's the final speed that he ends the race with. V final. So find V final. So we could do this in any order. We don't necessarily have to go down this way, T1, T3. So, but these are all the possible things they could ask for.
So 20 seconds is the total time?
Yeah, the 20 seconds is the total time, yeah. Yeah, see, it says total time of 20.
Oh, and where we know that the initial velocity is 0?
Nowhere. The initial velocity is not given. But I'm assuming if it's a sprint race,
Oh, okay.
you know, unless you jump the gun, in which case you are disqualified, right? You start the race running already. Right. Okay, so let's see how many equations we can come up. There's going to be a bunch of equations, right? We can determine the final velocity that he would have acquired here, right? What was the final velocity that he would have acquired? V, we can call that V2 by just simply using V initial plus A1 T1, right? Right? So that's the velocity that you would acquire after accelerating for a certain amount of time, right? So since this is 0, V2 is This is 3 times t1, but we don't know what t1 is, right? So that's the velocity that you would acquire in a time of t1 if you accelerate at 3. Now, what distance would you cover from here to here? That's d1, right? So then we could use this equation. We could say d1 is equal to this x initial is 0, v initial is also 0, right? So then it's just going to be half, a is going to be what? 3 t1 squared. So 3 over 2 t1 squared, right? Because v initial at the beginning is 0, x initial is 0, so then half a t, then a is 3. So then you cover distance of 3 halves t1 squared. That's d1. That's the distance you cover in the first stage. And that's all we know, right? So this equation gives us that, this equation gives us the final velocity. Now we can determine what distance you would cover if you ran at that speed v2 for constant speed, right? For 8 seconds. So what's d2 now? The distance you cover in the second stage is going to be the speed that you have, which is your v2, right? Times t2, because you're not accelerating, right? So then you have here d2 is going to be 3t1 times t2, which is 8 seconds, right? So labeling things really is helpful for this kind of problem. T2, T1, A1, A2, you got everything, you know. So then the D2 is going to be 24 T1. Okay? Now let's do the third stage. The second stage is easy. There's not much to do. You know? So the third stage, now we have the velocity that you have here is your initial velocity, which is going to be the same as V2, right? And then here, you're going to end with some final velocity, right? So what's going to be your final velocity? V2 plus A3 T3, right? Because here, you're still running at that same speed, right? And then you're accelerating A3, then we don't know the T3. So we know that the V final is going to be what? V2, which is going to be 3T1, plus A3 is what? We don't know. T3 we don't know. Well, too many unknowns there. 3T1 plus A3 T3. Okay, but we do know that the sum of the 3 times T1 plus T2 plus T3 is 20, right? So T1 plus T2 plus T3 is 20, but we're already given T2 is 8 seconds. So T1 plus T3 is what? 12 seconds. So let's try to see how many more equations I need. I have 1, 2. Oh, you know what? What else? We need an equation telling us that the total distance is 200, right? Yes. So I need another equation for D3. What's my D3? Distance covered in the third stage. It's going to be V initial T, right? So what's my V initial? It's V2, right? V2 T3 plus half A3 T3 squared, right? And then V2 is going to be 3T1. So V2 is your 3T1, then I substitute that there, then T3 plus half A3 T3. Oh my God, none of those we know. T1, T3 plus half A3 T3 squared. But we do know that the sum of the distances is 200. So D1 plus D2 plus D3 is 200. Is this solvable or too many unknowns? Well, let's see what we have here. D1 is going to be 3 halves T1 squared, right? So the sum of the distances is 200. So D1 is going to be 3 halves T1 squared. D2 is going to be 24 T1. D3 is going to be this crazy one, right?
Yeah.
So 3 T1 T3. And that's equal to 200, right?
Yeah.
Yeah, so D1 plus D2 plus D3 is equal to 200. And then we have the fact that T1 plus T3 is 12.
We only got two equations, but we have two variable with two squares.
T1 plus T3 is 12. That means I can say T3 is 12 minus T1. Then I can substitute that there, but then there's an unknown here.
Yes.
So it's
We still
unsolvable.
have two unknown variables.
Mm. Okay, you know what that means? The problem has to give us another piece of info. It either needs to give us the time of the first stage, or it needs to give us the distance of the second stage, or it can give us the distance of the third stage, or it can give us the final velocity. So there's some piece of information that's missing. In other words, with just the given unknowns, the sprinter has multiple choices of how to make this run in 20 seconds. That's what this is saying. He has different ways of accomplishing the 20-second run, unless you give it one more unknown, right? Because he could he could sprint at 3 for a long time, maintain constant speed, and then accelerate for a short time. You see? So when you have too many unknowns, that means that multiple ways can accomplish this case. So in order to capture one of those cases, some other piece of info has to be given. So we can say the sprinter finishes the race going at, what's a realistic goal? Because the sprinters really race their fastest at the end, right? So this realistic speed is what? What's the top speed of like Usain Bolt at the end of his race?
Can you go like 12,
I think they can run as fast as a cheetah, right? No? Almost
yeah,
close
he
to a
was.
cheetah. I was about to look up Google and I picked this up.
Yeah, I know.
Oh, this isn't gonna do Google for me.
Yeah,
23 miles per hour.
Huh?
23.35 miles per hour.
Okay, so that's about 16 meters per second. Realistic. So he finishes the race with 16 meters per second. Okay? Okay, then where we would put that? We would put here 16. See? That's gonna help us get rid of one more unknown, right? We can say, which unknown do we want to get rid of? Like A3, let's say, right? We can say A3 is 16 minus 3t1, right?
We don't know these three
Then A3 is gonna be what? 16 minus 3t1 over t3, but then t3 is 12 minus t1, right? And then my goal is to put this in here because then this equation will only have t1 as one variable, as only one unknown. Okay, now it's doable, right? Well, I guess this can cancel one of these, right? We can multiply everything by 2. That way we get rid of the 2 here. So it'll be 3t1 squared plus 48t1 plus 6t1, 12 minus t1 plus 16 minus 3t1, 12 minus t1. I multiplied everything by 2, so I got rid of this. This became 6t, this became 48, this became 3, and then this one become 400. Okay, now put that into solver and have it give you t1. Okay. Solve. It's going to be 3x squared plus 48x plus 6x times 12 minus x only one answer, 3 seconds. Yeah, I don't think you should have 2 answers here. Because that's it, there's only one way to accomplish this race. So T1 equals 3.0588 seconds. Well, once you get that, the whole piece of the puzzle is broken, right? Once you get that, then you can calculate T3, right?
Yeah.
Then you can calculate V2, which is the speed, the constant speed. V2 is 3 times T1. So V2 is just simply going to be this, right? 3 times T1. So since T1 was 3 seconds, 3 times that is 9. So that's his that's his constant speed that he's running at 9 meters per second. Gosh, that's fast. That's like 15 miles an hour.
Yeah.
God. Right? And okay, so after that, everything else we can calculate. D1 is 1.5 T1 squared. So D1 comes out 14.034 meters. And then D2 is 24 T1. So then it's just 24 times 73.4112 meters. And of course, D3 is going to be 200 minus these, right? So, I think that's it. Pretty much it solves everything. So, this one is a matter of labeling really well, drawing a nice picture, getting all the equations, putting everything together, and then eliminating all but one unknown, you know? Okay, now let me solve one similar to one of your homework questions, which involves it's the helicopter problem. This was a tricky one, even though people have it in their homework, and they have it, they even practice it together with their SI session, and then I give some variation of it on the test, and then they'll always make some mistake. Like for example, I might say something like this. After 10 seconds, the helicopter releases a bag of medicine, right, to the town that they're taking it to. So, how many seconds later? Okay. After, how many seconds later will the bag hit the ground, and what is its velocity when it hits the ground? Right? So if you've done that problem in the homework, you kind of know that the height function is given to you there for a purpose, because it allows you to find the initial height of the drop, right? What else does it allow you to do? It allows you to find the initial what of the drop? Huh? Velocity, right? Because when something's height is changing and it also drops an object, the object's velocity, initial velocity, will be the same as the height, right? So if my hand is going up and down, right? You see? As I'm going up and down, randomly I drop an object. Try to notice what the velocity, the initial velocity of that object is. You know? So what happened there? I dropped it while I was going down, I think. I dropped it when I was going up, I think. Maybe you can slow-mo that, right? So if you slow-mo it, you're gonna see the marker initially going up. If I dropped it while going up, right? What if I dropped it while going down? Okay? So now its initial velocity is what? Negative, right? So we tend to think when you drop something, it means the initial velocity is 0. Because the word drop we associate with drop like this. You see? And so when we see the word drop or release, you know, or we say, oh, it releases. Well, releases doesn't mean throw, right? That's what throws people off. Because the word drop and release is different than throwing something. So when you say the helicopter released the bag, people are going to say, oh, the initial velocity of the bag is 0. No. With respect to the helicopter, it's going to be 0 because you're releasing it. But if the helicopter is going down with respect to the ground, the bag is going to be going down also. But the person in the helicopter is going to say the initial velocity is 0 because with respect to them, they just dropped it. You see? So my hand is going down, right? If I release it, my hand is going to think the initial velocity is 0. You see? But my body is saying, oh no, the hand is going down. I see the marker also going down. You see? So the hand and the eyes are different in this case. It's a different reference frame. You see? So now, in order to find out in 10 seconds where is the bag, so you find h of 10, right? What does that give you? 100 times 0.8, 80. 300 minus 80 is what? 220 meters. So that means the helicopter's location after 10 seconds is 220 meters. What's the helicopter's velocity? H prime of t. That gives you the helicopter's velocity, right? So that's negative 1.6 t. And if I put 10 there, that's going to give me what? 16 meters per second, right? T is equal to 10. All right? So the initial velocity of the helicopter is 16. Therefore, the initial velocity of the bag that it releases is also 16, negative 16. That means this helicopter released the bag while it was going down. And you can tell it is going down, right? But sometimes you might not know in the beginning that it's going down. What if it's a weird function? You know, the teacher might give you a function like that. Well, how do you know if the helicopter is going down or up? Well, take the derivative, right? And then once you put the time in there, if the velocity is positive, the helicopter is going up. If the velocity is negative, the helicopter is going down, right? So it might be a weird driver, right? And the helicopter is doing this, right? So, okay, so in this case, it's going down, right? So then you do what? So now you know the initial velocity of the bag is negative 16 and the initial height of the bag is 220. So how do I answer that question? Which equation should I use? How many seconds will the bag hit the ground? What is its final velocity? I think the second equation again. Should I use meters here? Oh, this one was in meters, right?
Yeah.
If they tell you that this units is in meters, then you use the meters. So now here we're gonna put negative 4.9. Y final is what? When the bag hits the ground, Y final is 0. Y initial is what? 220. V initial is what? Negative 16, right? Why negative 9.8? Well, once you release the bag, the acceleration of the bag is negative 9.8 down. So it's speeding up. Okay, so then solve for that quadratic. Tell me what you get. Put it in your solver. From this point on, slowly and slowly, I'm gonna get more and more lazy, and then I'm gonna say, you put it in solver and tell me what the answer is.
You can go ahead. I don't use it yet.
Yeah, I don't want to hear I don't know how to use it yet. 2 weeks, brother, you better know how to use it.
It just showed up yesterday. Plug it.
Do you know how to use it? Well, this is where you ask. Yeah. Go to the solver. Clear. And now we're going to minus 16x.
I'm just gonna write this down first, and then I'm gonna go back and check.
That one
Is that
I'm
the
not sure
equation
of.
equals
but,
0
we
and
can.
the variable?
I don't know these
stuff.
ones.
I get that from F2.
Does it have it there?
Okay, because I was trying to write this earlier. I didn't know about the comma on the X.
Yeah.
It's 5.2.
5.26.
4.
See, 5.264. So the most common error that people will make when I ask this question is they'll put like this. 0 to 20 minus 4.9 t squared. What's the mistake they're making?
They assume it's dropping from
the initial velocity.
Yeah, because they use the equation to find the initial height, but they forgot that the take the derivative means the velocity, and which means the velocity of the bag, right? So when they do that, I go like this. So then I put this next to their test. Sorry, do homework next time. That means you should have known from the homework not to do that. Or what if they did this?
I'll forget the direction.
Yeah, so this person is a little bit better. They deserve maybe a little bit more partial credit, right? They took the derivative, but the sign is wrong. So it's like a sad face and a happy face, right? Okay, but be careful about directions, buddy. Right? So it's like this. Smile and it's sad. Okay, then once you get the time, how do you get the final speed? You're still not out of the woods, right? You gotta get this part correct. V final, negative 16. Negative 16 minus 9.8 this, right?
Yeah.
And whatever that is. So about 66, something like that. Nice. So over there, don't put positive 16, and of course don't put the initial as 0, you know. So all those things be wary of. Okay, guys. So have a good President's Day holiday. Oh no, we're gonna see each other tomorrow. What did I say? Lab 1 you're gonna turn in tomorrow. We're gonna do our first write-up lab. Okay, then you go to your President's Day holiday.